Morning, nerds. Today we have a sign that Thomas Wedlock made for me, so we're featuring his sign. And you notice it says good after morning. He said that way I can use it in the mornings or in the afternoon. So I thought that was pretty cute of him. And the collector of cones, because I told them a fun story of, oh, I didn't even catch it, that's a ruler. I thought that was like a sidewalk or something. So fun. A story about where I stole a cone and accidentally made chlorine gas and almost died. But anyway, so that's what that's about. So yeah, you are still nerds though. Okay, today we are going to be working on talking about complex zeros and the fundamental theorem of algebra, but you notice I got a piece of scrap paper up here. You don't need to write any of this. I'm just trying to show you some stuff, okay? I'm going to put a few graphs up. Like I said, you don't need to write any of this. In my second period, I did this on Desmos, but seeing as how I have yet to set up OBS Broadcaster to record screens, I'm just going to do them by hand. Alrighty? Alrighty. In this first one, I'm going to draw us a quadratic. In the second one, I'm going to draw a quadratic. And in the third one, you guessed it, another quadratic. Okay, picture's not drawn to scale, whatever. Here's what I would like to know from you. How many solutions does this have? He says dos, 2. Why 2? Not because it crosses the x-axis twice, we say this thing has 2 solutions, right? But we also talked about the fundamental connections that we talked about recently. We said that if k is a real number, a whole bunch of things were the same statement, saying that, rather than try to do them from memory, we said that k is a solution of the equation f of x equals 0. That's the same thing as saying k is a zero of the function. That's the same thing as saying k is an x-intercept of the function. And that's the same thing as saying x minus k is a factor of the function. Cool? Okay. What we would say here is that this quadratic has 2 distinct solutions. Distinct means different. How many x-intercepts does this quadratic have? Just 1. How many solutions does it have? Actually, by definition, we would say this has 2 solutions. It's called a repeated root. Because all quadratics have 2 solutions, like Jack just said a minute ago. I said, why does this have 2 solutions? He says, because it's quadratic. That's right. All quadratics have 2 solutions. So even though this has 2 solutions, they're the same number. It's a repeated root. How many x-intercepts does this graph have? 0 x-intercepts. How many solutions does it have? It still has 2 solutions. So even though it has no x-intercepts, it still has 2 solutions. So what's going on? Well, what's going on is our solutions are no longer real numbers. Our solutions would be complex. Cool with that? So Jack said, well, I know it has 2 solutions because it's a quadratic. Yeah. The fundamental theorem of algebra says whatever the degree of the polynomial is, that's how many solutions it has. And it specifically says they're complex. Time for a brain bomb. You might not have known this, but all numbers are complex numbers. Maybe we need to review what a complex number is. A complex number is any number written in the form a plus bi, where a is the real component and bi is the imaginary component. So there is a difference between imaginary numbers and complex numbers. Complex numbers have a real component and an imaginary component. Real numbers are just the numbers that you know and love. Imaginary numbers are like that. But I just told you that every single number, real or imaginary, is a complex number. all of them. For example, the number 3. 3 is a real number, but it's also a complex number. See? It's complex. Its imaginary component happens to be 0, but that doesn't change the fact that it's a complex number. And the number 2i. Yeah, this is an imaginary number, but it's also complex. See? It's kind of like how we say all squares are rectangles, but not all rectangles are squares. All real numbers are complex numbers. All imaginary numbers are complex numbers. Well, then I think the real question is, what is a complex number? This is just how they're written. What does it mean to be a complex number? That's the next big question, right? Where is my... Here's another piece of scrap. This will work. I'm going to draw a number line. You probably didn't know that every time you drew a number line, you were actually drawing a real number line. And every number on it represents a real number. Okay. Then where's the imaginary number line? It's here. This is the real number line. This is the imaginary number line. From geometry, how many dimensions does a line have? 1 dimension. This is a 2-dimensional space. It has a left-right component and an up-down component. So all real numbers are 1-dimensional numbers because they can be found on this 1-dimensional line. All imaginary numbers are 1-dimensional numbers because they can be found on this 1-dimensional line. Complex numbers are 2-dimensional numbers. The number 2 plus 3i is here in the complex plane. So complex numbers are 2-dimensional numbers. They simply have a second dimension to them. All real numbers fall on the real number line. They are 1-dimensional numbers where they don't have an imaginary component. They are still complex. For example, here's the number 1. That's 1 plus 0i. And here's the number 2i. 1 plus 2i. 2-dimensional. Has a vertical and a horizontal component. That is what complex numbers are. So now that we've discussed what they are, the next question would be, why do we even have them? Where do they even come from? It's simple. All quadratics have 2 solutions, right? That means there must be a way to get 2 answers from this setup. All quadratics have 2 solutions. So let's use some regular old algebra. Subtract 1 from both sides. And take the square root of both sides. Do you guys remember what happens every time you cancel a square with a square root? The plus or the minus. Yeah. Doing this creates a plus or a minus. And you go, great. But what is the square root of -1? Well, I'll tell you. It's a numeric value that our tiny human brains have trouble comprehending. They just struggle with it. So like any other number that we deal with, that we have trouble dealing with, we're going to use a symbol to represent that number's value. And yes, you have done this before. Here's a symbol that represents a number. Here's a symbol that represents a number. You don't know it, but here's a symbol that represents a number. You've heard of this number. You just didn't know that that was its symbol. The golden ratio. This is phi. This is the letter that mathematicians to represent the golden ratio. This is E, Euler's number, about 2.718-ish. This is pi, about 3.14-ish. So like many numbers that we deal with when we can't comprehend or even, what's even the word I want to use for this? Like fathom what that number could possibly be, we represent it with a symbol. By the way, this is also a symbol that represents something. See, we make a symbol to represent the value. So we use the imaginary unit I to represent the value of the square root of -1. So yeah, that is what imaginary numbers are. They are the square roots of negative numbers. They are the square roots of negative numbers. And because all quadratics have two solutions, there must be a way to get those solutions. We just needed to have a symbol to represent them. There it is. Okay? So it has two solutions, but it has no x-intercepts. I guess that means there's a difference between solutions and x-intercepts. Are all x-intercepts solutions? Yes. Are all solutions x-intercepts? No. This has two solutions and they are not x-intercepts. So under what circumstances do we get solutions that are not x-intercepts? When these solutions are complex. So if your solutions are complex or imaginary, let's say complex that have an imaginary component, they're solutions, but they are not x-intercepts. So that is the difference between the two concepts. Yes?
So for something to be a solution, or it has to be an x-intercept, or it has to be complex?
Okay, you started a question and then ended with a statement. In order for something to be an x-intercept, it must be a real solution. So all real solutions are going to be x-intercepts. Solutions are just solutions. Solutions are what would make the equation equal 0 if we plugged it in. But complex solutions that actually have an imaginary component will never be x-intercepts because they're in two-dimensional imaginary plane. They make the equation equal 0, which makes it a solution, but not an x-intercept. Wait a minute. Right here, if I said that this crossed at +1 and -1, we could say, remember when we were doing the whole bouncing crossing stuff? We could say that the factor here is x minus 1 and the factor here is x plus 1, right? Which means I could actually build my quadratic. This quadratic would be x plus 1 times x minus 1. And these factors are linear because you see their x's are power of 1. And this is how we got my solutions. But if I was just able to get solutions from this, I must be able to factor this. Well, the solutions were right there. So I guess that means that x squared plus 1 factors into x plus I and x minus I. And if we use that logic, x squared plus 2 factors also. Its solutions are plus or minus the square root of 2. And if I could factor using imaginaries and I could factor using irrational, I guess I could factor anything as long as I know the solutions. That's called the linear factorization theorem. It says you could factor anything. This word is not supposed to be teen, it's supposed to be then. if you know all of the solutions of a polynomial, then the linear factorization literally just writes out x minus solution over and over and over again. Factor anything you want. All polynomials must be able to factor into linear factors. Okay. So in our linear factorizations, you might have noticed that these all say z. Z is the letter that mathematicians use to represent complex numbers, lowercase z. So if I wanted to say that my solutions are 2 plus I and 2 minus I would say z sub 1 is 2 plus I and z sub 2 is 2 minus I. Instead of saying x equals. Because you can't really say x equals. That doesn't make much sense. How's x going to be an imaginary number? X is the real number line, right? Or complex number, I should say. So you should technically say z sub. Am I going to ever get on your case if you write x equals 2 plus I? No, I'm not. I'm just letting you know why there are z's in this box. So we have the fundamental theorem of algebra says all polynomials have exactly n solutions. They could be real, they could be complex, whatever. All polynomials can be factored into linear factors. Again, with real and or complex factors, okay? And then this box is the same box that we talked about a couple days ago where it said the fundamental connections that, you know, solutions were the same as x-intercepts, were the same as roots, and were the same as factors, right? The only difference is one of them is missing from this box because it says if k is a complex number. You might have noticed that x-intercept is missing from the box. And that's because complex numbers, by definition, as long as they have an imaginary component, are not on the x-axis. So they cannot be x-intercepts. Okay? Okay. Now, down here with these three examples, it says to write the polynomial function in standard form. That means do all the distributions and combining like terms. Identify the zeros, identify the x-intercepts. So I'm going to try to squeeze the zeros and x-intercepts up here so I can use this space down here for all the distributions. Let's start with zeros. When it's factored, we can see the zeros. It's what makes the inside of the parentheses equal 0. I'm even going to cheat, and I'm going to write x equals. Please know that I should technically say z equals. You know what? F it. I'm going to write z equals. Z equals positive or negative 2i. I can't say x equals positive and negative 2i. That doesn't make any sense. But those zeros are non-real zeros. And those are the only zeros. So what does that tell me about my graph? It has no x-intercepts. So because my quadratic, and it will be a quadratic because it's just two sets of parentheses, because my quadratic has no real solutions, it has no x-intercepts. We'll have a polynomial that does not touch the x-axis. Before I go on, I'm going to go ahead and put all three of these on here to make sure that I have enough space for all of them. For the next one, 3 parentheses tells me 3 zeros. One of them is real. X equals 5, but the other two, z equals plus or minus root 2i. Interesting. They both had 2 non-real solutions. That's interesting. And they were both plus or minus the same number. That's really interesting. What about x-intercepts? At x equals 5. Yep. We have an x-intercept at x equals 5. Because it's a real solution. All real solutions will be x-intercepts. Bless you. There are 4 sets of parentheses. That means there are 4 solutions. That doesn't mean there's 4 different solutions. It means there's 4 solutions. The reason why is because one of them is a repeated solution. We have x equals 3 as a repeated solution. Who remembers what that means for the graph? Adi? Yep. That means my graph will have a bounce at x equals 3 because it's a repeated, an even number of times. 0. But the other 2 zeros are plus or minus I. Again, they came in a pair, the same value, just one was positive, one was negative. It's almost like that is a fundamental part of the nature of these complex numbers. X-intercepts, the one real solution. Fun. All right. Let's go ahead and get our standard form of all 3 equations for A in blue. Could I take the time to write out all 4 of the distributions, combine my like terms? I could. But I would rather use an Algebra 1 concept. This creates the difference of 2 squares. By the way, a plus b and a minus b, regardless of what a and b are, these are called conjugates. Hopefully you've heard that vocabulary word in mathematics, conjugates. And when you multiply 2 conjugates, you always get perfect square minus perfect square. Always. Every single time. That's what happens when you do conjugates, when you multiply conjugates, like 1 plus root 2, 1 minus root 2. Those are conjugates. And when you multiply them, you get 5. I think. No, you get negative 3. But the point is, when you multiply 2 things where the only part that changed was the symbol in the middle of the 2 things, they're called conjugates. And we could do the same thing here. It says square the front, square the back, put a minus sign in between. Square the front, square the back, put a minus sign in between. Well, what is 2i squared? That's 2i times 2i. That's 4i squared. So I have x squared minus 4i squared. Where's that scrap paper? Did I already throw it away? Shame on me. Here's some scrap paper. Can you guys help me remember what is I again? What is I? Oh, it's a square root of negative 1. Okay, so I is a square root of negative 1 because the thing we just got was I squared. So let's go ahead and square both sides of this. And what we'll get is I squared is, oh snap, look at that, it's negative 1. How about that? So this is actually x squared plus 4 because I squared is negative 1. That's right, x squared plus 4 factors. There's its linear factorization. X minus 2i, x plus 2i. That's it in standard form. It's a quadratic that's been shifted up 4 units and points up. Of course, it has no x-intercepts. Part B. Hold on, we got to pause this for this conversation. Now that I've completely destroyed a child, I can get back to teaching. Part B. Part B. And not only did I show you that your math knowledge was poor, I argued it using religion. God, I'm smart. Okay, so part B. Part B. This is a pair of conjugates. I am so happy with myself right now. I love being right. Okay, this x minus 5 is coming along for the ride for now. So we're just going to write this x plus 5, but check this out. These are conjugates. Square the front, square the back, put a minus sign in between. So square the front, square the back, put a minus sign in between, And what happens when you square root 2? You get 2. And what happens when you square I squared? So can we agree that this right here equals negative 2? So this is squaring this root 2 gets me a 2. Squaring this I gets me a negative 1. So this is negative 2. So what this actually gives me is x minus 5 times x squared plus 2. Ta-da! Yes. Oh gosh, no. I is not underneath that radical symbol. You are not prepared to deal with square root of I right now. Which is not the same as saying the fourth root of I. So the square root of I is not the square root of the square root of negative 1. I know that sucks that it didn't work like that, but those exponent rules that you think are true only hold true for real numbers sometimes. So is there a square root of I? In the real number system, the square root of the square root is the fourth root. Yes. Yes, Adi? Yeah. We should learn it sometime when we're doing trigonometry. After we're finished with precalculus. Keep asking. When is that going to happen? I don't know. Usually it happens semester 2. But that was in precalc honors, so we'll have to find out. Oh, yeah, this year for sure. Yeah, we'll do it this year. You're asking me if the square root of I, all quantities squared, is I? That's... If the I was inside. Okay, yeah, if I was inside the square root bar. Hold on. Let's write what you're saying. He wants to know if this is this I. That's what he's asking. That's one of its values. It has more than one value. You'll see when we get to that material. Because it requires a knowledge of trigonometry to pull it off. Okay? Now, because this is AP, I'm going to hope and pray that you guys could distribute and don't need to see that work. There it is. And let's go ahead and tackle that last one. Purple? Yeah, I'm holding the purple pen. C. I'm going to save some space, and we're going to pretend I wrote this out again. Actually, I'll write it out again.
Okay, now I clicked completely at least.
Okay, this is me multiplying two conjugates. This is not. So once again, because it is AP, I'm going to hope and pray that you guys can do x minus 3 times x minus 3, and you could easily get to x squared minus 6x plus 9. Because negative 3 plus negative 3 is negative 6, and negative 3 times negative 3 is positive 9. This, multiplying conjugates, is going to square the front, square the back, put a minus sign in between. But we've already said multiple times that I squared is negative 1. So what does this actually say? It actually says x squared minus 6x plus 9 times x squared plus 1. And you're going, ew, I don't want to have to do all the distributions. There's going to be 6 things, and there's going to be like terms, and blah, 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 blah. Yes, you are very correct with all the blah, blah, blahs. So you can either write it out horizontally, or you could do something that Mrs. Hess showed me. I don't know if any of you remembers her. She retired from Venice Mill years ago. Yeah? We're not finished yet, but yeah.
So if I squared equals negative 1, wouldn't you do exponents first, and then that would become 1, so it would be...
No. Exponents first, right. So it would be negative 1. So it would be minus negative 1.
But negative 1 times negative 1
Is positive 1.
Yeah.
Right. That's why it says plus 1. You see it? Here's what it actually says. No, it's x squared minus negative 1. This is I squared. So it's minus this thing's value, and this thing's value is -1. So it's minus -1. That's how we get the +1. Anyway, I'm trying to show you something that Miss Hess taught me. What is it? X squared minus 6x plus 9? And we're going to multiply it to x squared plus 1. This is a way of doing distribution vertically, like they're long numbers. It actually is much easier to do, and it takes up less horizontal space, and you don't have to keep track of your like terms because you line up your like terms. It works like this. 1 times 9 is positive 9. 1 times -6 is -6, but there's an x. 1 times x squared is x squared. X squared times 9, that's 9x squared, right? So line it up with its like terms. X squared times -6x is -6x to the third. And x squared times x squared is x to the fourth. Then you just add straight down, and you have your polynomial. X to the fourth minus 6x to the third plus 10x squared minus 6x plus 9. It's much faster. It's not even a trick. No, it's distribution. That's not a trick. In fact, it's not. Why do you think that multiplication works the way it does? It's not a trick. 3 times 3 is 9. 3 times 2 is 6. 3 times 1 is 3, right? 2 times 3 is 6, right? But it's not actually 2 times 3. It's 20 times 3, which is 60, right? So, and 20, it's actually not 2 times 2 here. It's not even, it's actually 2 times 20, but it's actually 20 times 20. It's 400, right? So 400 goes right here. See how I'm lining up my like terms? And this 2 times this 1 is not 2 times 1. It's not even 20 times 1. It's 20 times 100, which is 2,000. And then you add straight down. You see, in early mathematics, they were cheating you when they told you to put that 4 right here. Because what they weren't teaching you is that it was actually a 400. Okay? So no, it's not a trick. This is actually why multiplication works the way it does. What you were taught by putting a 4 there, that's the trick. Anyway, we already got our result. It was right here. So that is x to the fourth minus 6x to the third plus 10x squared. I missed a square in my answer. Minus 6x plus 9. So earlier, when I kind of alluded to the fact that the complex numbers coming in pairs, one's always a plus and one is always a minus, and I said it's kind of like it's part of the nature of complex solutions. Yeah, it is. They're called complex conjugate zeros. All complex solutions come in conjugate pairs. I'm trying to talk over the people that are talking while I'm teaching. All complex solutions come in conjugate pairs. It is literally 100% impossible to have a single complex solution. Not possible. Why, Mr. M? Because all complex solutions are the result of you taking the square root of a negative number. And canceling a square with a square root creates the plus or the minus. So they must always come in a conjugate pair. Always. So if I tell you 1 plus I is a solution, you know 1 minus I is also a solution. It's impossible to have one without the other. They have to both exist. Cool with that? You didn't even have to write it. It's right there. But they have to both exist. If one of them exists, they both exist. All right. Then let's get to the last thing I wanted to do with you today, and that is this first question. We're going to write a polynomial function of minimum degree. That means don't go nuts, just the smallest degree possible that this thing could actually have. In standard form, yuck, that means I'm going to have to do all the distributions. With real coefficients, don't worry, I will never ask you to deal with a function that has complex or imaginary coefficients, whose zeros include these numbers. So we know that x equals -3 is a solution. We know that x equals 4 is a solution. And we know that z equals 2 minus I is a solution. What else do we know? 2 plus I is also a solution. Because it's impossible to have just 2 minus I. That means we also have to have the 2 plus I as well. This thing has 4 solutions, so what kind of polynomial of minimum degree are we talking about? What's that minimum degree? Yeah, it's a 4th degree polynomial, a quartic. It has 4 zeros. That means there's 4 sets of parentheses in its linear factorization. We are looking for a 4th degree polynomial. So let's write out that linear factorization. You ready? F of x is, well, if -3 is its solution, then its linear factorization is x plus 3. If positive 4 is a solution, then its linear factorization is x minus 4. Are you guys aware that when you have to wrap a set of parentheses inside of a set of another parentheses, like this sucks to look at, so instead we write it like this in mathematics? Good. X minus this complex number, x minus its conjugate. And let me tell you what is not fun to distribute. Those. They are not fun to distribute. This isn't bad. That's just x squared minus x minus 12. That's pretty easy. This part, this is not bad at all. This quadratic will be x squared minus x minus 12. And this is also going to get me a quadratic because this is 2 solutions, right? The question is, what would the quadratic have been? Okay. Can we agree that if we were solving a quadratic, it would have said x equals at the end? It wouldn't have said z equals? Can we at least agree to that? I'm glad one person can agree to that. Anyway, what we have is x equals 2 plus or minus I. Those are the 2 quote-unquote solutions. Technically, they should say z equals, but we all know that if we were solving the quadratic, it would have said x equals eventually, right? But wait a minute. If these 2 solutions were the result of me using SAD MEP to isolate x, I should be able to do that in reverse order to get back the quadratic that these came from. And that plus or minus I, that was the result of me taking the square root of -1. Because this is AP, at some point in time, I'm going to have to imagine that you could do x minus 2 times x minus 2, and that you're not going to write x squared plus 4 because that makes me want to poke my eyes out. What is I times I, just in general? You don't have to give me a number value. I squared. What is negative I times negative I? Oh, still I squared. Oh. Oh, but what is I squared equal to? -1. Oh. Oh, look here. If I just add 1 to both sides, then I have the quadratic that produces those 2 complex results. This quadratic has no real solutions. It has 2 complex solutions. Those 2 complex solutions have to be 2 plus or minus I. So what did the question actually want us to do? It actually wanted us to do this. No, it didn't want you to do that. She whispered to kill ourselves. I have dad ears. That's how I heard it. I can hear your head bouncing off a tile floor from 3 houses down. What you actually needed to do was distribute this mess to get it in standard form. And that has 9 distributions. So instead of trying to write those out horizontally and running out of space and looking for like terms, I'm going to go over to my scrap paper. Well, don't worry, it's in the video. And we'll just distribute this way. This way all my like terms are always lining up because it's so much nicer. 5 times negative 12 is negative 60. 5 times negative x is negative 5x. And 5 times x is 5x squared. Negative 4x times negative 12 is positive 48x. That's its like term, so that's where I'm going to write it. Negative 4x times negative x is positive 4x squared. And negative 4x times x squared is negative 4x to the third. X squared times negative 12 is negative 12x squared. See, I'm just making the like terms line up. X squared times negative x is negative x to the third. And x squared times x squared is x to the fourth. And we can just add straight down now and have the result. X to the fourth minus 5x to the third. That's 9 minus 12 minus 3x squared plus 43x minus 60. And that is our polynomial in standard form. I'm going to write it on my paper now. There it is, but in case you wanted to see it again, that was how we got there. I just didn't have the space to show it. Nerds.